Step outside on a clear night, far from the glow of city lights. Look up. What do you see? A canopy of stars scattered like diamonds across an ocean of black. Beautiful, peaceful, familiar. But there's something deeply wrong with this picture, something that should terrify you to your core. That darkness between the stars, that comforting black backdrop that makes the points of light so magnificent, shouldn't exist. If our universe truly works the way we think it does, if it's infinite and eternal and filled with countless stars stretching in every direction forever, then that night sky should be blazing with light. Not just bright, but blindingly, overwhelmingly, impossibly bright. As bright as the surface of the sun itself. Yet here we stand, wrapped in cosmic darkness, and most people never stop to wonder why. This isn't just a curiosity for astronomers, or a puzzle for physicists. This is a mystery that cuts to the heart of everything we think we know about reality itself. And the answer, when we finally understood it, revealed truths about our universe so profound and terrifying that they changed everything. The problem was first clearly stated in 1823 by a German astronomer named Heinrich Olbers, though others had glimpsed it before him. Picture the logic of what became known as Olbers' paradox. If the universe stretches infinitely in all directions, and if it has existed forever, and if it's uniformly filled with stars, then no matter which direction you look in the night sky, your line of sight should eventually hit a star. Think about it this way. Imagine you're standing in the middle of an infinite forest. The trees stretch endlessly in every direction. No matter where you look, eventually your gaze will hit a tree trunk. You won't see any gaps, any empty spaces between the trees, because somewhere along every possible line of sight, there's a tree blocking your view. The entire horizon would be nothing but tree trunks, wall to wall. Now apply this same reasoning to the cosmos. If stars are scattered throughout infinite space, and if the universe has had infinite time for light to travel from even the most distant stars, then every single point in the night sky should be occupied by the brilliant surface of some star somewhere. The entire dome of the heavens should blaze like a continuous sheet of stellar fire. But it doesn't. The sky is dark, profoundly, mysteriously, impossibly dark. This darkness is so familiar to us that we barely notice it. We've grown up with dark nights. Our ancestors told stories by firelight under dark skies. Poets have written about the beauty of stars twinkling against the black void. But that familiar darkness is actually screaming at us, trying to tell us something fundamental about the nature of reality. The paradox becomes even more disturbing when you consider the numbers. There are hundreds of billions of stars in our galaxy alone, and there are hundreds of billions of galaxies visible to our telescopes. That's roughly 10 to the 22nd power stars that we can observe, 10 followed by 22 zeros, a number so vast that if you tried to count them, spending 1 second on each star, you'd need longer than the current age of the universe to finish, and that's just what we can see. If the universe is truly infinite, then there are infinitely many more stars beyond our observation. Infinite stars, infinite galaxies, infinite light sources all shining into the cosmos. By rights, their combined radiance should turn night into day, should make the darkness between stars impossible. Yet darkness persists. Every night without fail, the sun sets and the familiar black sky emerges, punctuated by scattered points of light. This darkness is so reliable, so consistent, that we base our entire understanding of day and night on it. Our biological rhythms depend on it. Our sense of time and season flows from it. But what if that darkness is an illusion? What if it's trying to tell us something we're not ready to hear? The first attempts to solve Olbers' paradox were ingenious, but ultimately wrong. Some suggested that cosmic dust might absorb the light from distant stars, creating the dark patches we see. Others argued that perhaps the universe wasn't infinite after all, that there might be a finite number of stars, not enough to fill every point in the sky with light. Still others wondered if the human eye simply wasn't sensitive enough to detect the faint glow that should be there. Each of these explanations seemed reasonable at first glance. Dust does absorb light. The universe might be finite. Human vision does have limits. But as scientists probed deeper, each explanation crumbled under scrutiny. Dust that absorbed enough starlight to darken the sky would heat up from all that absorbed energy and begin to glow itself, creating the same problem in a different form. A finite universe might explain some darkness, but calculations showed that even a relatively small cosmos with a modest number of stars should still produce a much brighter sky than what we observe. And instruments far more sensitive than the human eye still detected the same mysterious darkness. The paradox remained unsolved for more than a century after Olbers first stated it clearly. Throughout the 1800s and into the early 1900s, the dark night sky continued to mock our understanding of cosmic reality. It sat there above us every night, beautiful and peaceful, and utterly impossible according to our best theories about how the universe should work. What made the paradox even more maddening was its simplicity. This wasn't some esoteric problem requiring advanced mathematics or exotic physics. Any child old enough to wonder about the stars could understand the basic logic. If there are stars everywhere, and light travels from stars, then why isn't the sky bright everywhere? The question was simple. The answer would turn out to be revolutionary. As the 20th century dawned, new technologies and new ways of thinking about space and time began to emerge. Powerful telescopes revealed that some of the fuzzy patches in the night sky weren't clouds of gas, but entire galaxies, island universes containing billions of stars. Suddenly, the scale of the cosmos expanded dramatically. Instead of one galaxy containing all the stars, there were countless galaxies, each a stellar city in its own right. This discovery should have made Olbers' paradox worse. More galaxies meant more stars, which should have meant more light, which should have made the sky even brighter. But the darkness persisted, as deep and mysterious as ever. Scientists began to realize that the solution to the paradox might not lie in astronomy alone, but in the fundamental nature of space, time, and cosmic evolution. The dark night sky wasn't just asking us to count stars or measure distances. It was asking us to reconsider everything we thought we knew about the universe itself. The darkness between the stars was about to teach us that our cosmos had a beginning, that it was expanding, that it might have an end. It was about to reveal that the familiar night sky was actually a window into the deepest questions of existence. Questions about whether the universe would last forever, whether life could persist indefinitely, whether the darkness we see now might be a preview of an eternal cosmic night stretching into an unimaginably distant future. Standing under that star-filled sky, surrounded by the ancient darkness, we were looking at one of the universe's greatest riddles. And once we began to understand the answer, we would never see the night the same way again. The comforting black spaces between the stars would become windows into cosmic truths, both beautiful and terrifying, revealing a universe far stranger and more fragile than we had ever dared to imagine. For nearly a century after Heinrich Olbers clearly stated his paradox, the brightest minds in science wrestled with the mystery of the dark night sky. The problem seemed so straightforward that surely there had to be a simple explanation. Surely something obvious was being overlooked. The darkness above our heads became a challenge, a puzzle that demanded solving, and scientists responded with ingenuity, creativity, and ultimately, a series of elegant failures that would teach us as much about the universe as any correct answer. The first and most intuitive explanation seemed almost too obvious to be wrong. Space, reasoned many astronomers, must be filled with dust and gas that absorbs starlight before it can reach Earth. After all, we could see dark lanes cutting through the bright band of the Milky Way, clear evidence that cosmic dust could block light from distant stars. Perhaps the entire universe was suffused with this light-absorbing material, creating a cosmic fog that dimmed the radiance from faraway stellar furnaces. This dust hypothesis felt satisfying because it matched everyday experience. We knew that fog could obscure distant lights, that smoke could dim the sun, that even clear air could scatter and absorb light over long distances. Mountains disappeared into haze. City lights faded with distance. Why shouldn't the same principle apply on cosmic scales? The mathematics seemed to support this idea initially. If you assumed that space contained even a tiny amount of dust per cubic meter, and you calculated how much starlight would be absorbed over the vast distances between galaxies, the numbers worked out reasonably well. The dust could indeed dim the sky enough to explain why we don't see a blazing celestial dome every night. But as scientists dug deeper into the physics, a fatal flaw emerged. Dust doesn't simply absorb light and make it disappear. When dust particles absorb energy from starlight, they heat up. And when objects heat up, they begin to glow with their own thermal radiation. The cosmic dust that was supposed to solve the paradox by absorbing starlight would inevitably become a source of light itself. Think about this process more carefully. Every grain of cosmic dust floating in space would be constantly bombarded by light from nearby stars. Each photon of starlight that struck a dust particle would transfer its energy to that particle, causing its temperature to rise. As billions and billions of photons from countless stars hit each speck of dust, that dust would grow hotter and hotter until it began to radiate energy back into space. The cruel irony was that in a universe filled with infinite stars shining for infinite time, the dust would eventually reach thermal equilibrium. It would heat up until it was radiating away energy at exactly the same rate it was absorbing energy from starlight. And at that equilibrium temperature, the dust would be glowing at roughly the same temperature as the stellar surfaces that were heating it. Instead of solving Olbers' paradox, cosmic dust would simply transform it. Rather than seeing the bright surfaces of distant stars directly, we would see the bright glow of heated dust particles scattered throughout space. The night sky would still be blazingly bright, just for a different reason. The darkness would remain unexplained. This realization was both frustrating and illuminating. It showed that you couldn't solve the paradox simply by invoking some mechanism to block or absorb starlight. In a universe with infinite energy sources shining for infinite time, that energy had to go somewhere. And wherever it went, it would eventually manifest as heat and light. The darkness demanded a more fundamental explanation. The second major attempt to solve the paradox focused on the possibility that the universe might not actually be infinite. Perhaps there were only a finite number of stars scattered throughout space, not enough to create the wall-to-wall brilliance that Olbers had envisioned. This finite star hypothesis seemed reasonable because it attacked one of the key assumptions underlying the paradox. If you stood in a finite forest, after all, you would indeed see gaps between the trees. Your line of sight in many directions would extend past the last tree and into empty space beyond. Similarly, if space contained only a finite number of stars, many lines of sight would extend past the last star and into the cosmic equivalent of empty space, explaining the dark patches we observe in the night sky. Early estimates of stellar numbers seem to support this possibility. In Olbers' time, astronomers could see perhaps 6,000 stars with the naked eye. Even with the best telescopes of the early 1800s, the total number of visible stars numbered in the hundreds of thousands. These seemed like large numbers, but were they large enough to fill the entire sky with light? Careful calculations suggested they were not. If you distributed even 1,000,000 stars randomly throughout space and calculated how much of the sky they would cover when viewed from Earth, the answer was a tiny fraction. Most of the celestial sphere would remain dark, with scattered bright points marking the locations of individual stars. This matched what people actually observed, providing an appealingly straightforward solution to the paradox. But this explanation, too, would crumble as astronomical knowledge advanced. Through the 1900s and into the 20th century, more powerful telescopes revealed fainter and fainter stars. The Milky Way alone was found to contain not thousands or millions, but hundreds of billions of stars. Beyond our own galaxy, telescopes revealed countless other galaxies, each containing billions of stars of their own. The universe was far more densely populated with stars than anyone had imagined. Even conservative estimates of stellar numbers yielded totals that should have been more than sufficient to create the bright night sky predicted by Olbers' paradox. The finite star hypothesis collapsed under the weight of observational evidence. More sophisticated versions of this approach tried to account for the actual distribution of stars in space. Rather than assuming stars were uniformly scattered, astronomers recognized that they were clustered into galaxies, which were themselves clustered into groups and superclusters. Perhaps this hierarchical structure could explain the darkness. If stars were gathered into isolated galaxies, separated by vast empty regions, then many lines of sight might extend through the empty spaces between galaxies without ever encountering a star. The night sky would show bright patches where we looked through distant galaxies and dark patches where we looked into the voids between them. This clustering hypothesis was more sophisticated than earlier attempts, but it still faced a fundamental problem. Even if galaxies were separated by empty space, there were so many galaxies scattered throughout the observable universe that the statistical argument remained compelling. Random lines of sight should still encounter enough distant galaxies to fill in most of the dark spaces. Moreover, detailed observations showed that even the apparently empty regions of space weren't completely dark. Sensitive instruments could detect a faint background glow coming from every direction, suggesting that the universe was indeed more uniformly filled with light sources than the clustering hypothesis would predict. A third class of explanations focused on the limitations of human perception and astronomical instruments. Perhaps the night sky actually was bright with the combined light of infinite stars, but that brightness was simply too faint for us to detect. Our eyes might not be sensitive enough to perceive the glow, or the light might be spread so evenly across the sky that it didn't stand out against the background. This sensitivity hypothesis had some merit. Human vision is notoriously poor at detecting uniform illumination. We see by contrasts, by differences in brightness between adjacent regions. A sky that glowed uniformly with a faint light might indeed appear dark to our eyes, especially if that glow was much dimmer than the bright points of individual stars. Astronomers tested this idea by using increasingly sensitive instruments to measure the brightness of apparently empty patches of sky. They found that these regions were indeed slightly brighter than perfect darkness, confirming that there was some sort of background illumination filling the universe. But the brightness was nowhere near what Olbers' paradox predicted. Even accounting for the limitations of human vision and early instruments, the night sky was orders of magnitude dimmer than it should have been in an infinite, eternal, star-filled universe. The sensitivity hypothesis could explain why a moderately bright sky might appear dark to casual observation, but it couldn't explain why the sky was genuinely, measurably dark when examined with precise instruments. As each proposed solution failed, the paradox began to take on an almost mythical quality in scientific circles. It seemed to mock every attempt at explanation, revealing flaws in reasoning that had initially seemed airtight. The dark night sky became a stubborn puzzle that refused to yield to conventional thinking. Some scientists began to suspect that the solution would require abandoning one or more of the fundamental assumptions underlying the paradox. Maybe the universe wasn't infinite in extent. Maybe it hadn't existed forever. Maybe the laws of physics worked differently on cosmic scales than they did in terrestrial laboratories. These were radical thoughts in the 1900s, when the prevailing view of the cosmos was static and eternal. Most astronomers believed that the universe had always existed in roughly its current state, with stars and galaxies scattered throughout infinite space according to unchanging physical laws. The idea that the universe might have had a beginning, or that space itself might be evolving, seemed almost heretical. Yet the dark night sky continued to whisper that something was wrong with this picture. Every clear evening brought a fresh reminder that our understanding of cosmic reality was incomplete. The familiar darkness above our heads was trying to tell us something profound about the nature of space, time, and existence itself. The solution, when it finally came, would require insights that went far beyond astronomy. It would demand new ways of thinking about the relationship between space and time, about the possibility that the universe itself might be evolving, about the deep connections between the larger scales of reality and the most fundamental questions of physics. The dark night sky wasn't just asking us to count stars or measure distances. It was challenging us to rethink our most basic assumptions about the cosmos we inhabit. And that challenge would ultimately lead to one of the most profound revolutions in scientific understanding that humanity has ever experienced. The year 1929 changed everything. That was when Edwin Hubble, working with the massive 100-inch telescope at Mount Wilson Observatory, made an observation so startling that it would revolutionize our understanding of the cosmos and finally point toward a solution to Olbers' paradox. What Hubble discovered was that the universe itself was moving, expanding, growing larger with every passing moment. And this cosmic expansion would turn out to be the key to understanding why the night sky is dark. Hubble wasn't looking for cosmic expansion when he made his groundbreaking discovery. He was simply trying to measure the distances and velocities of galaxies beyond our own Milky Way. Using a technique based on observations of certain types of variable stars, he had already established that many of the fuzzy patches scattered across the night sky were actually entire galaxies, island universes containing billions of stars. But when Hubble began measuring how fast these galaxies were moving relative to Earth, he found something completely unexpected. Nearly every galaxy he observed was moving away from us. Not just moving, but racing away at tremendous speeds. Galaxies that were farther from us were moving away faster than nearby ones. The pattern was so consistent and so surprising that it demanded an explanation. The key insight came from examining the light itself. When Hubble analyzed the spectrum of light coming from distant galaxies, he found that familiar patterns of absorption lines created by various chemical elements were shifted toward longer, redder wavelengths. This redshift was the cosmic equivalent of the Doppler effect that makes an ambulance siren sound lower in pitch as it speeds away from you. Just as sound waves from a receding source are stretched to lower frequencies, light waves from receding galaxies are stretched to longer, redder wavelengths. The amount of redshift directly indicates how fast the source is moving away. And what Hubble found was that virtually every galaxy in every direction showed this telltale redshift, indicating that they were all receding from our position in space. Even more remarkable was the relationship between distance and recession velocity. Galaxies twice as far away were moving away twice as fast. Galaxies 3 times farther were moving 3 times faster. This linear relationship, now known as Hubble's law, suggested something profound about the nature of space itself. If every galaxy was moving away from every other galaxy at a rate proportional to their separation, then space itself had to be expanding. It wasn't that galaxies were flying apart through static space, like debris from an explosion. Rather, space itself was stretching, carrying the galaxies along with it like raisins in an expanding loaf of bread. This concept of expanding space was difficult to grasp initially. We're accustomed to thinking of space as an empty stage on which cosmic events play out, a fixed background that doesn't participate in the action. But Einstein's theories of relativity had already suggested that space and time were dynamic quantities that could bend, warp, and evolve. Hubble's observations provided the first direct evidence that space was indeed changing on the largest scales. The implications for Olbers' paradox were immediate and profound. In an expanding universe, light from distant galaxies doesn't simply travel through static space on its journey to Earth. Instead, it travels through space that is stretching during the entire time the light is in transit. And when space stretches, it stretches the light waves traveling through it. Consider a photon of light emitted by a star in a distant galaxy billions of years ago. That photon begins its journey with a specific wavelength, perhaps in the visible range that our eyes can detect. But as the photon travels through expanding space, the expansion stretches its wavelength, making it redder and redder as the journey progresses. For the most distant galaxies, this stretching effect is so extreme that light originally emitted in the visible range is stretched far beyond what human eyes can see. Blue light gets stretched to green, then to red, then to infrared, and eventually to radio wavelengths. The farther the galaxy, the more its light is redshifted, and the more of that light is pushed beyond the limits of visible perception. This cosmological redshift provides an elegant partial solution to Olbers' paradox. Even if the universe contains infinite galaxies shining for infinite time, much of their light is redshifted so far toward longer wavelengths that it becomes invisible to our eyes and even to many of our instruments. The darkness of the night sky is partly an illusion created by our limited ability to detect highly redshifted light. But the expanding universe does more than just redshift light beyond visibility. It also dilutes the energy of that light in a more fundamental way. As space expands, the energy density of radiation filling that space decreases. Photons don't just get redshifted, they also become less numerous per unit volume as the volume of space itself grows. Think about this dilution effect more carefully. Imagine a region of space containing a certain number of photons. As that region expands, the same number of photons is spread over a larger volume, reducing the energy density. Additionally, each individual photon loses energy as its wavelength is stretched by the expansion. The combination of these effects means that the energy density of radiation in the universe decreases rapidly as space expands. This dilution has profound consequences for the brightness of the night sky. Even if distant galaxies are shining with tremendous luminosity, their light is both redshifted to longer wavelengths and diluted to lower energy densities by the time it reaches us. The farther the galaxy, the more its light is affected by these processes, and the dimmer it appears to earthbound observers. The expanding universe also introduces a more subtle but equally important effect, related to the finite speed of light. When we look at distant galaxies, we're seeing them not as they are now, but as they were when the light we're detecting first left them. For galaxies billions of light years away, we're seeing them as they were billions of years ago. In an expanding universe, this look-back time means we're observing distant galaxies when they were younger and when the universe itself was smaller and denser. The most distant galaxies we can see are being observed in a cosmic environment very different from the one that exists today. They're embedded in a universe that was hotter, denser, and evolving more rapidly than our current cosmic neighborhood. This temporal aspect adds another layer to the solution of Olbers' paradox. We're not just looking out through space when we observe the night sky, we're also looking back through time. The light we detect from distant sources carries information about cosmic conditions that existed billions of years ago, not about the current state of those distant regions. The combination of expansion, redshift, and look-back time creates a complex relationship between cosmic distance and observable brightness. Distant galaxies appear dim, not just because they're far away, but because we're seeing them in a younger, different universe, and because their light has been stretched and diluted during its long journey through expanding space. Perhaps most remarkably, the expanding universe also implies that there's a limit to how far we can see, even in principle. Because space has been expanding since the universe began, and because light has a finite speed, there's a maximum distance from which light has had time to reach us. This distance, known as the cosmic horizon, defines the boundary of the observable universe. Beyond the cosmic horizon lie regions of space whose light hasn't had time to reach us yet, no matter how long we wait or how sensitive our instruments become. These regions contribute no light to our night sky simply because we're causally disconnected from them. The observable universe has a finite size, not because space itself is finite, but because we can only see as far as light has had time to travel since the universe began. This horizon effect provides another piece of the solution to Olber's paradox. Even if the universe beyond our horizon contains infinite galaxies, shining with infinite luminosity, those galaxies can't contribute to the brightness of our night sky because their light hasn't reached us yet. The darkness we observe is partly a consequence of the finite age of the universe and the finite speed of light. The expanding universe revealed by Hubble's observations thus attacks Olber's paradox from multiple directions simultaneously. Cosmological redshift pushes much distant light beyond the range of human vision. Energy dilution reduces the brightness of distant sources. Look back, time shows us galaxies as they were in the past rather than as they are now. And the cosmic horizon limits our view to a finite region of space. Each of these effects contributes to making the night sky dimmer than it would be in a static, infinite, eternal universe. Together, they provide a compelling explanation for much of the darkness we observe. But even the expanding universe doesn't completely solve the paradox. Detailed calculations show that while expansion significantly reduces the brightness of the night sky, it doesn't reduce it quite enough to match observations. The expanding universe was clearly part of the answer, but it wasn't the complete answer. Something else was needed to fully explain the profound darkness that surrounds the scattered points of starlight. That something else would turn out to be even more fundamental than cosmic expansion. It would require us to abandon the assumption that the universe has existed forever and to confront the possibility that everything we see around us had a definite beginning in time. The dark night sky wasn't just telling us that space was expanding. It was whispering that time itself might have a starting point, that the cosmos might be much younger than anyone had dared to imagine. And that whisper would soon become a roar as astronomers uncovered evidence that the universe began in a cataclysmic event that would come to be known as the Big Bang. If the expanding universe was a revelation, what came next was nothing short of a cosmic revolution. As astronomers in the early 20th century grappled with the implications of Hubble's discovery, they began to realize that an expanding universe pointed towards something even more profound and unsettling. If galaxies were racing away from each other today, and if this expansion had been going on for a long time, then logic demanded a startling conclusion. In the past, everything in the universe must have been much closer together. And if you trace this expansion backward far enough, you arrived at a moment when everything that exists was compressed into an infinitesimally small point. The universe had a beginning. This idea was so radical, so fundamentally at odds with prevailing scientific and philosophical thought, that many astronomers initially resisted it. For centuries, the dominant view had been that the cosmos was eternal and unchanging, a static arena in which stars and planets moved, but which itself remained constant through infinite time. The notion that the entire universe might have popped into existence at a specific moment in the past seemed to venture dangerously close to theology and away from the solid ground of scientific materialism. But the mathematics was inexorable. If space was expanding now, and if the laws of physics had remained constant through time, then reversing the expansion led inevitably to a moment of infinite density and temperature, a cosmic singularity from which all space, time, matter, and energy emerged. This moment, initially derided by skeptics as the Big Bang Theory, would eventually become the cornerstone of modern cosmology. The Big Bang provided the final, crucial piece needed to solve Olbers' paradox completely. An expanding universe explained why distant light was redshifted and diluted, but a universe with a finite age explained something even more fundamental. It explained why there simply hadn't been enough time for light from the most distant regions of space to reach us. Consider the implications carefully. If the universe is 13.8 billion years old, as current observations suggest, then light from objects more than 13.8 billion light-years away hasn't had time to reach Earth yet. No matter how many stars and galaxies exist beyond that distance, no matter how brilliantly they shine, their light is still traveling toward us through space and won't arrive for millions or billions of years. This creates what astronomers call the particle horizon, the boundary between the regions of space we can observe and the regions we cannot. The particle horizon isn't a physical barrier. It's simply the limit imposed by the finite age of the universe and the finite speed of light. Beyond this horizon lies the unobservable universe, a realm that might contain infinite galaxies and infinite stars, but which contributes no light to our night sky because that light hasn't had time to reach us. The existence of a particle horizon provides an elegant and complete solution to Olbers' paradox. Even if the universe beyond our horizon is infinite and filled with stars, those stars can't make our night sky bright because we're causally disconnected from them. The darkness between the stars isn't the absence of light sources. It's the absence of light that has had time to travel from those sources to our location. This temporal solution to the paradox is both beautiful and unsettling. Beautiful because it resolves a century-old mystery with mathematical precision. Unsettling because it reveals that our cosmic perspective is fundamentally limited. We can never observe the majority of the universe, no matter how long we wait or how advanced our technology becomes. The observable universe is just a tiny bubble surrounding us in what might be an infinite cosmic ocean. But the finite age of the universe does more than just solve an astronomical puzzle. It fundamentally changes our understanding of cosmic evolution and the nature of time itself. In a universe with a beginning, everything we observe has a history, a story of development from simpler to more complex states. The stars we see in the night sky weren't always there. They formed from clouds of gas and dust that were themselves created in earlier epochs of cosmic history. The chemical elements that make up planets and living things were forged in the nuclear furnaces of stellar cores and scattered into space when those stars died. The galaxies we observe are the products of gravitational collapse and cosmic evolution operating over billions of years. This evolutionary perspective reveals why the early universe looked so different from today. In the first few 100 million years after the Big Bang, there were no stars at all, just vast clouds of hydrogen and helium gas slowly collapsing under their own gravity. The first stars that formed were massive, short-lived giants that burned through their nuclear fuel quickly and died in spectacular supernova explosions. These early stellar deaths were crucial for cosmic evolution because they scattered heavier elements into space, providing the raw materials needed for subsequent generations of stars and planets. the universe gradually became enriched with carbon, oxygen, silicon, iron, and all the other elements essential for complex chemistry and life. The finite age of the universe means we're living in a specific epoch of cosmic history, a time when stars are still forming, galaxies are still evolving, and the expansion is still stretching space. This epoch won't last forever. The universe is aging, evolving, moving towards states very different from what we observe today. Current models suggest that star formation will eventually cease as the universe uses up its supply of hydrogen gas. Existing stars will burn out one by one over trillions of years, leaving behind a cosmos populated only by dead stellar remnants, black holes, and scattered subatomic particles. The bright star-filled universe we see today is a temporary phase in cosmic evolution, a brief moment of brilliance between the dark simplicity of the early universe and the dark emptiness of the far future. This temporal perspective adds profound meaning to the darkness of the night sky. The spaces between the stars aren't just empty because light hasn't had time to arrive from distant sources. They're also previews of what the entire universe will look like in the unimaginably distant future, when the last stars have burned out and darkness has reclaimed the cosmos. The finite age of the universe also resolves a subtle version of Olber's paradox that might arise even in an expanding cosmos. Even if cosmological redshift pushes distant light beyond visible wavelengths, sensitive instruments can detect radiation at all frequencies. If the universe were infinitely old, even redshifted light from infinite sources should eventually fill space with detectable radiation at all wavelengths. But in a universe with a finite age, there's a limited amount of time for light to accumulate. Stars have only been shining for a finite period, and even their combined output integrated over cosmic history produces a finite amount of radiation. The background glow predicted by Olber's paradox requires infinite time to build up, but our universe simply hasn't existed long enough for that process to reach completion. The Big Bang Theory not only explains why the night sky is dark, it also makes specific predictions about what we should observe instead of the blazing brightness Olbers expected. If the universe began in a hot, dense state and has been expanding and cooling ever since, then space should be filled with the remnant radiation from that primordial fireball. This cosmic microwave background radiation was predicted by Big Bang theorists in the 1940s and discovered by accident in 1965. It appears as a faint glow coming from every direction in space, the afterglow of creation itself, redshifted by billions of years of cosmic expansion from visible light to microwave frequencies. The existence of this background radiation provides powerful confirmation of the Big Bang Theory and adds another layer to our understanding of cosmic darkness. The universe isn't completely dark, it's filled with this ancient light from the moment when atoms first formed and space became transparent. But this light has been redshifted so far beyond visible wavelengths that it's invisible to human eyes, contributing to the darkness we perceive. The finite age of the universe thus provides both the final solution to Olber's paradox and a window into cosmic destiny. The darkness between the stars tells us that the universe had a beginning, that we're living in a specific moment of cosmic history, and that the brilliant stellar display surrounding us is temporary. This temporal perspective transforms our relationship with the night sky. When we look up at the stars, we're not just seeing distant suns scattered through space, we're seeing the products of cosmic evolution, the temporary residents of a universe that began in darkness, blazed into light, and will eventually return to darkness again. The dark spaces between the stars aren't empty voids, they're windows into cosmic time. They show us both where the universe came from, a state of darkness before the first stars formed, and where it's going, a future state of darkness after the last stars die. The familiar night sky becomes a meditation on temporality, evolution, and the precious fragility of the light-filled epoch in which we find ourselves. Standing under the stars, surrounded by the ancient darkness, we're witnessing one of the most profound truths about reality. The universe is not eternal and unchanging, but dynamic and finite, a cosmic story with a beginning, a middle, and eventually an end. The darkness teaches us that we're living in the middle chapters of that story, in an age of stars and galaxies, and possibilities that won't last forever. This knowledge is both humbling and inspiring. Humbling because it reveals the temporary nature of everything we see around us. Inspiring because it shows that we're part of an extraordinary cosmic adventure, witnesses to and participants in the ongoing evolution of reality itself. The night sky's darkness becomes not a void to be feared, but a reminder of our place in the grand narrative of existence. The universe is not actually dark. This revelation, discovered in 1965 by two radio astronomers who were simply trying to eliminate static from their antenna, would revolutionize our understanding of cosmic history and add the final piece to the Olbers paradox puzzle. What Arno Penzias and Robert Wilson found by accident was that space itself is glowing with the faint afterglow of creation, a whisper of ancient light that fills every cubic centimeter of the cosmos. They called it the cosmic microwave background radiation, and it represents perhaps the most important discovery in 20th century astronomy. This faint glow is the stretched and cooled remnant of the brilliant light that filled the universe when it was only 380,000 years old, a baby cosmos just emerging from its earliest, most violent phase of existence. To understand this cosmic glow, we need to journey back to the very beginning of time and trace the evolution of light itself through cosmic history. In the first moments after the Big Bang, the universe was so hot and dense that matter existed only as a seething plasma of subatomic particles. Protons, electrons, and photons were locked in a constant dance of absorption and emission, with light unable to travel more than microscopic distances before being scattered by free electrons. The early universe was opaque, like the interior of a star. Light existed everywhere, blazing with incredible intensity, but it couldn't propagate freely through space. Instead, it was constantly absorbed and re-emitted by the dense soup of charged particles that filled all of reality. This epoch, known as the photon epoch, lasted for hundreds of thousands of years as the universe expanded and cooled. But expansion changes everything. As space grew larger, the density of matter decreased and temperatures dropped. Eventually, about 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. This moment, called recombination, marked one of the most important transitions in cosmic history. When recombination occurred, the universe suddenly became transparent. Free electrons, which had been scattering light in all directions, were now bound into atoms and could no longer interact strongly with photons. For the first time since the Big Bang, light could travel freely through space without being immediately absorbed or scattered. The result was a cosmic flash, a moment when the trapped light of the early universe was suddenly released, to shine freely through space. This light, blazing with the heat of the primordial fireball, began an epic journey that continues to this day. As the universe expanded, this ancient light was stretched to longer and longer wavelengths, cooling from brilliant visible light to infrared, then to microwave frequencies. Today, 13.8 billion years later, this light still fills the universe. But it has been redshifted so far that it's invisible to human eyes, detectable only with sensitive radio and microwave instruments. What was once the brilliant glow of a universe-sized furnace is now a faint whisper of radiation with a temperature just 2.7 degrees above absolute zero. This cosmic microwave background is remarkably uniform, glowing with almost exactly the same intensity in every direction we look. This uniformity tells us that the early universe was filled with light of extraordinary brightness and consistency. If we could somehow see microwave radiation with our eyes, the entire night sky would glow with a soft, even radiance, brighter than the light of the full moon. But we can't see microwaves directly, and this is crucial for understanding why the night sky appears dark to us. The cosmic microwave background is there, filling every corner of space with the afterglow of creation, but it's been redshifted far beyond the range of human vision. The universe is glowing all around us with ancient light, but that glow is invisible to our eyes. This invisibility provides a profound new perspective on Olbers' paradox. The night sky isn't actually dark in an absolute sense. It's filled with radiation from the Big Bang, a background glow that permeates all of space. But this glow has been shifted to frequencies we can't perceive, creating the illusion of darkness between the visible stars. If our eyes could detect microwave radiation, Olbers' paradox would be solved in the most literal way possible. The entire sky would indeed be bright, glowing uniformly with the light of the early universe. The darkness we perceive is partly a limitation of our sensory apparatus, not a fundamental property of the cosmos. The cosmic microwave background also helps us understand the relationship between past and present in cosmic evolution. The light we detect today was emitted when the universe was vastly different from its current state. At the time of recombination, space was about 1,000 times smaller than it is now, making the universe much hotter and denser. This ancient light carries information about cosmic conditions that existed billions of years before the first stars formed. It shows us the universe as it was in its infancy, before gravity had time to gather matter into the complex structures we see today. The tiny variations in the background radiation, detected by sensitive instruments, represent the seeds from which all cosmic structure would eventually grow. These primordial fluctuations, imprinted on the cosmic microwave background, would eventually become the galaxies, stars, and planets we observe today. The faint variations in the ancient glow map out the early distribution of matter that would later collapse under gravity to form the cosmic web of filaments and voids that characterizes large-scale structure in the modern universe. The discovery of the cosmic microwave background also resolved a deeper version of Olbers' paradox that emerges when we consider all forms of electromagnetic radiation, not just visible light. Even if visible light from distant stars is redshifted beyond perception, those same stars emit radiation at many wavelengths. Radio waves, infrared light, ultraviolet radiation, and other forms of electromagnetic energy should all contribute to a diffuse background glow-filling space. In an infinite, eternal universe filled with stars, this background radiation should build up to enormous levels over time. Stars have been emitting energy at all wavelengths for cosmic ages, and that energy has to go somewhere. Even accounting for cosmic expansion and redshift, the accumulated radiation from infinite sources should create detectable background light at all frequencies. But observations show that while there is indeed background radiation at various wavelengths, it's dominated by the cosmic microwave background from the Big Bang, rather than by accumulated starlight. This tells us that the universe simply hasn't existed long enough for stellar radiation to build up to the levels predicted by the classical version of Olbers' paradox. The cosmic microwave background thus serves as both evidence for the Big Bang theory and the final proof that the universe has a finite age. The dominance of primordial radiation over accumulated starlight shows that cosmic history began with a hot, dense state, rather than an eternal sequence of stellar generations. Perhaps most remarkably, the cosmic microwave background allows us to observe the universe at its moment of transition from opacity to transparency. When we detect this ancient radiation, we're seeing the last moment when light and matter were in thermal equilibrium, the final instant before the universe became transparent and light could travel freely through space. This makes the cosmic microwave background a kind of cosmic horizon, the farthest back in time we can observe using electromagnetic radiation. Before recombination, the universe was opaque, and no light from those earlier epochs can reach us directly. The cosmic microwave background represents the earliest baby picture of the universe we can ever hope to obtain through conventional astronomy. The uniform glow of this ancient light also helps explain another aspect of cosmic darkness. If the early universe was so bright and uniform, why didn't that brightness persist as the universe expanded? The answer lies in the nature of expansion itself and the conservation of energy. As space expands, the energy density of radiation decreases much more rapidly than the energy density of matter. Photons lose energy as their wavelengths are stretched, and they also become less numerous per unit volume as space grows. This double effect means that radiation-dominated epochs in cosmic history give way to matter-dominated epochs as the universe expands and cools. Today, we live in a matter-dominated universe where the energy density of matter far exceeds the energy density of radiation. The cosmic microwave background, despite filling all of space, contains only a tiny fraction of the total energy in the universe. Most cosmic energy is now locked up in matter, particularly in the mysterious dark matter that outweighs ordinary matter by a factor of 5 to 1. This transition from radiation domination to matter domination explains why the early universe was so bright, while the current universe appears relatively dark. The primordial glow that once blazed with incredible intensity has been diluted and redshifted by billions of years of expansion, leaving only a faint whisper of its former brilliance. The cosmic microwave background thus provides the final chapter in our understanding of cosmic darkness. The night sky is dark to our eyes because the dominant source of cosmic radiation, the afterglow of the Big Bang, has been redshifted far beyond visible wavelengths. The universe is filled with light, ancient light from the moment of its birth, but that light is now invisible to human perception. This invisible glow transforms our understanding of the spaces between stars. Those apparently empty regions aren't truly empty, they're filled with the faint echo of creation itself. Every cubic centimeter of space contains thousands of photons from the cosmic microwave background, ancient travelers that have been journeying through the universe since before the first stars formed. When we stand under the night sky, we're immersed in this ocean of primordial light. It streams through our bodies, fills our lungs, bathes every atom of our being in the afterglow of the Big Bang. We can't see it or feel it, but it connects us directly to the moment of cosmic birth, making us participants in the ongoing story of universal evolution. The darkness between the stars is thus revealed to be an illusion of perception rather than a fundamental property of space. The universe glows with ancient light, whispers with the echo of its own creation, and fills every corner of reality with the faint but persistent reminder that everything we see around us emerged from a cosmic dawn billions of years ago. Even with the cosmic microwave background filling space with ancient light, even with the expanding universe and finite cosmic age explaining much of the darkness we observe, there remains something profoundly unsettling about the vast emptiness that separates the stars. When we truly grasp the scale of this emptiness, when we comprehend just how isolated each point of light really is in the cosmic ocean, the darkness takes on an almost overwhelming quality that speaks to the fundamental loneliness of existence itself. The numbers are staggering beyond human comprehension. Our nearest stellar neighbor, Proxima Centauri, lies 4.2 light-years away. To put this distance in perspective, imagine shrinking the sun to the size of a marble. On this scale, Earth would be a grain of sand orbiting about 3 feet away, and the nearest star would be another marble located 800 miles distant. The space between these marbles would be almost perfectly empty, containing perhaps a few atoms of hydrogen gas scattered across those hundreds of miles. This is the reality of interstellar space. The distances between stars are so vast that if you could travel at the speed of light itself, it would take years to cross the void between neighboring stellar systems. And light speed represents the ultimate speed limit of the universe, the fastest that information or matter can possibly travel according to our best understanding of physics. But the emptiness extends far beyond the spaces between individual stars. Our entire galaxy, the Milky Way, contains roughly 400 billion stars, yet it's still mostly empty space. If you could somehow remove all the stars from our galaxy while leaving their positions marked, you'd have 400 billion tiny points of light scattered throughout a disk 100,000 light-years across. The vast majority of the galactic volume would contain nothing but thin clouds of gas, cosmic dust, and the occasional wandering planet ejected from its home system. Even more dramatic is the emptiness between galaxies. While interstellar space contains at least some matter, a few atoms per cubic centimeter of hydrogen and helium gas, intergalactic space is far more desolate. Between galaxy clusters, the density of ordinary matter drops to less than 1 atom per cubic meter. These cosmic voids, spanning hundreds of millions of light-years, represent some of the most empty regions in the known universe. To appreciate this level of emptiness, consider that the best laboratory vacuums on Earth contain billions of atoms per cubic centimeter. The space between galaxies is 1 trillion times emptier than the best vacuum human technology can create. It's a void so perfect, so utterly devoid of matter, that it approaches the theoretical limit of nothingness while still being part of our physical reality. This cosmic emptiness isn't just a curiosity for astronomers, it's fundamental to understanding why the night sky is dark. Even if the universe contained infinite stars and galaxies, the vast distances between them ensure that most lines of sight from Earth extend through empty space. When you look up at the night sky, most of your gaze is piercing through these cosmic voids, regions where there's simply nothing to emit light. The structure of the universe itself contributes to this emptiness. Rather than being uniformly distributed throughout space, matter is organized into what astronomers call the cosmic web. Galaxies are strung along filaments of dark matter like beads on invisible strings, separated by enormous voids that contain almost no galaxies at all. This web-like structure means that much of the universe's volume is occupied by these dark, empty regions. These cosmic voids aren't just empty of stars and galaxies, they're also remarkably devoid of the dark matter that dominates the universe's mass. While dark matter filaments connect galaxy clusters and provide the scaffolding on which ordinary matter condenses, the spaces between these filaments are largely empty even of this invisible material. The voids represent regions where the cosmic web is stretched so thin that almost nothing exists. The formation of this cosmic web structure ensures that darkness dominates the universe on large scales. As the universe evolved from the nearly uniform conditions of the early cosmos, gravity amplified tiny density fluctuations into the large-scale structure we observe today. Matter flowed out of underdense regions and into overdense ones, creating a network of filaments surrounding vast, empty spaces. This process of structure formation is still ongoing. Cosmic voids continue to expand as matter flows out of them and into the surrounding filaments and galaxy clusters. The universe is becoming more and more structured with time, which means it's also becoming more and more empty in the regions between structures. The emptiness of cosmic voids has profound implications for any civilizations that might exist within them. A galaxy located in the center of a large void would see a night sky almost completely devoid of other galaxies. Such a civilization might conclude that their galaxy was the only one in the universe, surrounded by infinite empty space. only the most sensitive instruments would detect the faint glow of distant galaxy clusters, marking the edges of their cosmic prison. This scenario isn't just theoretical. Astronomers have discovered galaxies in void centers that are indeed isolated by hundreds of millions of light-years from their nearest neighbors. These lonely islands of stars exist in cosmic environments so empty that their inhabitants, if any exist, would have a fundamentally different perspective on the universe than we do. The emptiness also affects the evolution of galaxies themselves. Galaxies in dense environments interact frequently with their neighbors, triggering bursts of star formation, galactic mergers, and other dramatic events. But galaxies in voids evolve more slowly and peacefully, undisturbed by the gravitational chaos that characterizes denser regions. This environmental dependence means that the darkness between galaxy clusters isn't just empty space. It's space where cosmic evolution proceeds at a different pace. The voids represent regions where the universe remains closer to its primordial state, less processed by the violent interactions that shape galaxies in denser environments. Perhaps most remarkably, the cosmic voids are expanding faster than the overall expansion of the universe. While regions containing galaxies and dark matter are held together by gravity, the voids have so little matter that nothing can resist their expansion. They grow larger with time, making the universe increasingly dominated by empty space. This accelerating emptiness is one of the most striking features of cosmic evolution. As time passes, the universe becomes more and more void-dominated, with islands of matter separated by ever-growing oceans of nothingness. The darkness between structures isn't static, it's actively expanding, claiming an ever larger fraction of cosmic volume. The temperature of these empty regions adds another dimension to their desolation. Far from any stars or galaxies, cosmic voids are among the coldest places in the universe. The only source of heat is the cosmic microwave background radiation, which maintains a temperature of just 2.7 degrees above absolute zero. In the deepest voids, far from any source of starlight, the temperature approaches this cosmic minimum. This extreme cold means that any matter in the voids exists in exotic states rarely found elsewhere in the universe. Hydrogen gas in these regions has temperatures measured in fractions of a degree, creating conditions where quantum effects become important even for ordinary atoms. The voids represent natural laboratories for studying matter under the most extreme conditions of emptiness and cold. The magnetic fields in cosmic voids are similarly extreme. While galaxies and galaxy clusters have magnetic fields thousands of times stronger than Earth's, the voids have fields so weak they're barely detectable. These regions represent some of the most magnetically quiet environments in the cosmos, spaces where charged particles can travel for billions of years without encountering significant magnetic forces. Even the flow of time might be subtly different in these empty regions. According to Einstein's theory of relativity, time passes slightly faster in regions of weaker gravitational fields. Since cosmic voids contain so little matter, their gravitational fields are extremely weak, meaning that time flows marginally faster there than in denser regions. An observer in a cosmic void would age slightly faster than someone living in a galaxy cluster, though the effect is too small to measure directly. The emptiness of cosmic voids also affects the propagation of light and other forms of radiation. While photons travel in straight lines through empty space, their paths can be bent by gravitational fields. In dense regions of the universe, this gravitational lensing is common, with light from distant sources deflected by intervening galaxies and dark matter structures. But in cosmic voids, there's so little matter that gravitational lensing effects are minimal. Light travels through these regions almost completely undeflected, making voids windows of exceptional clarity for observing the distant universe. Ironically, The emptiest regions of space provide some of the clearest views of cosmic history. The vast scale of cosmic emptiness also has implications for the search for extraterrestrial intelligence. If civilizations exist in void galaxies, they would face extraordinary challenges in detecting or communicating with other civilizations. The distances involved are so vast that even light signals would take hundreds of millions of years to cross the voids. This cosmic isolation means that civilizations in different parts of the universe might remain forever unknown to each other, not because they don't exist, but because the emptiness between them is so vast that communication becomes practically impossible. The darkness of the night sky reflects not just the absence of light, but the profound isolation that characterizes existence on cosmic scales. Standing under the night sky, looking up at the scattered points of starlight, we're seeing the rare exceptions to cosmic emptiness. Each star represents a tiny island of warmth and light in an ocean of cold, dark vacuum. The spaces between them aren't just empty, they're actively expanding, growing larger and emptier with each passing moment. This expanding emptiness transforms our understanding of cosmic destiny. The universe isn't just cooling and darkening as it ages, it's also becoming more and more dominated by empty space. The future cosmos will be characterized not by the brilliant galaxies we see today, but by the vast, cold, empty voids that already dominate cosmic volume and will only grow larger with time. The darkness of the night sky holds within it a prophecy of cosmic doom so terrifying that when astronomers first glimpsed its implications, many refused to believe what their own data was telling them. What they discovered in the late 1990s would fundamentally change our understanding not just of cosmic history, but of cosmic destiny. The universe wasn't just expanding, it was accelerating, driven by a mysterious force that would eventually tear apart everything we see and plunge the cosmos into an eternal darkness far more profound than anything Olbers could have imagined. The discovery began with an attempt to measure how cosmic expansion was slowing down. Since the Big Bang, astronomers assumed, the expansion of space had been gradually decelerating as the gravitational pull of matter throughout the universe acted as a cosmic brake. By studying distant supernovae, stellar explosions so bright they could be seen across billions of light years, astronomers hoped to measure exactly how much this deceleration was affecting the expansion rate. What they found instead defied every expectation. The distant supernovae were fainter than they should have been if expansion was slowing down. They appeared to be farther away than predicted, as if space itself were stretching faster now than it had in the past. The universe wasn't decelerating at all. It was accelerating, expanding faster and faster with each passing moment. This discovery required the existence of something that had never been directly observed before, a component of the universe that didn't just fail to provide gravitational attraction, but actually created gravitational repulsion. Astronomers named this mysterious component dark energy, and it represents perhaps the most profound puzzle in modern cosmology. Dark energy appears to be a property of space itself, becoming stronger as space expands. Unlike matter, which becomes less dense as the universe grows larger, dark energy maintains constant density even as new space is created. This means that as the universe expands, the total amount of dark energy increases, providing an ever stronger push that accelerates the expansion. Currently, dark energy comprises about 68% of the total energy in the universe. It outweighs ordinary matter by more than 2 to 1, and even dominates the mysterious dark matter that makes up most of the universe's mass. We live in a universe where the dominant component is something we don't understand, something that's driving cosmic evolution toward a fate more desolate than any previous generation of astronomers had imagined. The implications for cosmic darkness are profound, and terrifying. As dark energy continues to accelerate expansion, galaxies will be carried away from each other at ever-increasing speeds. Eventually, distant galaxies will be receding so fast that their light will be redshifted completely out of the observable universe. One by one, the galaxies we see in the night sky today will fade from view, disappearing beyond the cosmic horizon as space expands faster than light can travel. This process has already begun. The most distant galaxies visible to our telescopes are receding at significant fractions of the speed of light. In the far future, as expansion continues to accelerate, even nearby galaxies will be carried beyond our ability to observe them. The Andromeda Galaxy, currently approaching us and destined to collide with the Milky Way in about 4 billion years, represents one of the last major galactic encounters our cosmic neighborhood will experience. After the Milky Way and Andromeda merge, and after a few other nearby galaxies join the resulting system, our local group of galaxies will find itself increasingly isolated. The expansion of space will carry all other galaxies so far away that they disappear from view entirely. Future astronomers living in this merged galaxy will look out at a night sky containing only the stars of their own system, surrounded by perfect cosmic darkness. This cosmic isolation represents a kind of observational horizon beyond which no information can travel. Galaxies carried away by accelerating expansion become causally disconnected from our location, unable to send signals that could ever reach us. The observable universe shrinks, not because space itself has boundaries, but because accelerating expansion creates an ever-tightening bubble of observability around each galaxy. The process doesn't stop with galactic isolation. Dark energy operates on all scales, and as it continues to strengthen, it will eventually overcome gravitational binding on smaller and smaller scales. Galaxy clusters will be torn apart first, with individual galaxies scattered into the expanding void. Then galaxies themselves will be disrupted, their stars flung into the darkness as dark energy overcomes even stellar gravitational attraction. In the most extreme scenarios, dark energy could eventually overcome the forces holding atoms together, leading to what cosmologists call the Big Rip. In this ultimate fate, every structure in the universe, from galaxy clusters down to subatomic particles, would be torn apart by runaway expansion. Space itself would expand so rapidly that no force in nature could resist its pull. Even if expansion doesn't reach such extreme levels, the long-term future remains bleak. Current models suggest that star formation will cease within the next trillion years as the universe uses up its supply of hydrogen gas. Existing stars will burn out one by one, with the longest-lived red dwarf stars surviving for trillions of years before they too exhaust their nuclear fuel. The universe of the far future will be populated mainly by stellar remnants, white dwarf stars, neutron stars, and black holes scattered through an ever-expanding and ever-darkening cosmos. These dead objects will slowly cool toward absolute zero as they radiate away their remaining heat into the cosmic void. Even the longest-lived of these remnants will eventually decay through quantum processes operating over unimaginable timescales. The black holes that form from the most massive stars will be among the last objects to survive in this dying universe. But even black holes aren't eternal. Stephen Hawking showed that they slowly evaporate by emitting radiation, with larger black holes lasting longer than smaller ones. The supermassive black holes at the centers of galaxies will persist for 10 to the 100th power years. But even they will eventually disappear in flashes of radiation. After the last black hole evaporates, the universe will enter what cosmologists call the heat death phase. Space will be filled with a thin soup of elementary particles, photons, and quantum fields, all at nearly absolute zero temperature. No complex structures will remain, no stars will shine, no planets will orbit, no life will exist. The cosmos will have reached maximum entropy, a state of perfect thermal equilibrium where no further evolution is possible. This ultimate fate represents darkness on a scale that makes our current night sky seem brilliantly illuminated by comparison. The spaces between stars that appear empty to us today will seem almost crowded compared to the ultimate emptiness that awaits. The universe will have expanded so much that the average density of matter will be far lower than the best vacuum we can create in laboratories today. The cosmic microwave background that currently fills space with the afterglow of the Big Bang will be redshifted to such long wavelengths that its energy becomes negligible. Even this last remnant of the universe's fiery birth will fade into undetectable oblivion, leaving space truly and completely dark for the first time since the cosmos began. But perhaps most disturbing is the timescale on which this cosmic death will unfold. The universe is currently 13.8 billion years old, a span that encompasses all of recorded history and more. Yet this represents only the tiniest fraction of cosmic future time. The era of star formation will last 1,000 times longer than the current age of the universe. The era of stellar remnants will last 1 billion trillion times longer than that. And the era of black hole evaporation will dwarf even those vast timescales. From our current perspective, living in what cosmologists call the stelliferous era, we exist during a brief moment of cosmic brightness, sandwiched between two eternities of darkness. The universe began dark and will end dark, with only a relatively short period in between when stars could form and shine, and create the islands of warmth and light that make life possible. This temporal perspective transforms our understanding of cosmic significance. The brilliant galaxies we see scattered across the night sky represent a temporary phase in cosmic evolution, a brief flowering of complexity and light that will fade as surely as spring gives way to winter. We're living during the cosmic equivalent of late summer, when the harvest is abundant, but the first hints of approaching winter are already visible in the lengthening shadows. The acceleration of cosmic expansion also affects our ability to understand the universe itself. As distant galaxies disappear beyond the cosmic horizon, future astronomers will lose access to crucial information about cosmic history and structure. They'll be unable to observe the cosmic microwave background, unable to detect distant supernova, unable to map the large-scale structure of the universe. In effect, accelerating expansion will gradually erase the evidence for the Big Bang and cosmic evolution. Future civilizations living in isolated galaxies billions of years from now may conclude that their galaxy represents the entire universe, static and eternal, surrounded by infinite empty space. They'll lack the observational evidence needed to reconstruct the dramatic history of cosmic expansion and structure formation that we're privileged to observe today. This erasure of cosmic history represents another form of darkness, an informational darkness that will eventually hide the truth about universal origins and evolution. The accelerating expansion that makes distant galaxies disappear also makes cosmic knowledge disappear, creating a kind of intellectual horizon beyond which certain truths become permanently unknowable. Standing under the night sky today, we're witnessing a universe at a unique moment in its evolution. The darkness between the stars hints at the much more profound darkness that awaits, but it also frames the temporary brilliance that makes our current cosmic epoch so special. The scattered points of starlight we see overhead represent a phenomenon that won't last forever. Islands of nuclear fire burning against the growing dominance of dark energy and cosmic expansion. The night sky's darkness thus becomes a memento mori, a reminder of cosmic mortality and the precious fragility of the light-filled universe we inhabit. It whispers of a future when all the galaxies will have faded from view, when all the stars will have burned out, when even the black holes will have evaporated, leaving behind only the vast, cold, empty darkness that represents the universe's ultimate destiny. This knowledge is both terrifying and beautiful. terrifying because it reveals the temporary nature of everything we see around us. Beautiful because it shows that we're living during an extraordinary moment in cosmic history, witnesses to phenomena that won't be visible forever. The darkness teaches us to appreciate the light while it lasts, to marvel at the temporary miracle of stars and galaxies and the brief cosmic springtime that made our existence possible. To truly appreciate the gift of cosmic darkness, we must imagine the alternative. What if Olbers had been right? What if the night sky blazed with the combined light of infinite stars, turning every moment into a cosmic noon brighter than the surface of the sun? This thought experiment isn't just academic curiosity, it's a journey into a universe so hostile to life that our very existence proves the cosmos has properties we should find both remarkable and terrifying. Picture stepping outside on what should be a peaceful evening, only to be blasted by light so intense it instantly burns your retinas. There is no night, no darkness, no respite from the searing radiance that pours down from every direction. The entire dome of the sky glows with the fury of a stellar surface, radiating energy at temperatures of thousands of degrees. This is the universe that classical physics predicted. A cosmos where infinite stars fill space so completely that darkness becomes impossible. The temperature alone would make such a universe uninhabitable. If every point in the sky radiated like the surface of a star, then Earth would be receiving energy from all directions simultaneously. Our planet would heat up until its surface temperature matched that of the cosmic background, roughly 5,000 degrees Celsius. Oceans would boil away instantly. The atmosphere would be stripped away by thermal motion. The rocks themselves would melt and eventually vaporize under the relentless bombardment of radiation. No planet in such a universe could maintain the delicate thermal balance necessary for liquid water, let alone the complex chemistry required for life. Surface temperatures would be so extreme that even the most heat-resistant molecules would break apart. The carbon-based chemistry that underlies all known life forms would be impossible, with chemical bonds destroyed as quickly as they could form. But the problems with a bright night sky extend far beyond temperature. The intensity of radiation would create other effects that make life even more impossible. With light streaming from every direction at stellar intensities, the concept of shadows would disappear entirely. There would be no protected spaces, no shielded environments where delicate biological processes could unfold without being disrupted by overwhelming energy flux. Photosynthesis, the process that powers most life on Earth, depends on plants absorbing a controlled amount of solar energy while being protected from excessive radiation. In a universe with a bright night sky, the energy flux would be so intense that it would destroy the molecular machinery of photosynthesis before it could function. Rather than powering life, the omnipresent radiation would sterilize any world it touched. The electromagnetic spectrum would be flooded at all wavelengths. Radio communication would be impossible because the background noise from cosmic radiation would drown out any signals. The radio telescopes we use to study the universe would detect nothing but static from the overwhelming glow of infinite stellar sources. Our ability to understand the cosmos through astronomy would be severely limited or eliminated entirely. Even more fundamental problems would emerge from the physics of such a universe. The enormous energy density required to make the entire sky bright would create gravitational effects that would fundamentally alter the structure of space and time. According to Einstein's equations, energy and matter curve space-time, and the energy density needed for Olbers. Bright sky would curve space so severely that the universe might collapse under its own gravitational field. The thermal radiation filling such a universe would also interact with itself in ways that create additional complications. At the temperatures required to make the sky bright, photons would have enough energy to create particle-antiparticle pairs when they collided. The universe would be filled not just with overwhelming light, but with a seething plasma of particles constantly being created and destroyed by high-energy radiation interactions. This plasma would be so dense and energetic that it would be opaque to light, creating a paradox within the paradox. The very brightness that Olbers predicted would create conditions so extreme that the universe would become opaque again, preventing the light from propagating freely. The bright night sky would defeat itself, creating a cosmic environment even more hostile to observation and understanding than our current dark cosmos. From a biological perspective, a universe with infinite stellar brightness would preclude not just life as we know it, but any conceivable form of complex organization. The high-energy radiation would constantly break apart molecules, preventing the formation of the large, stable structures that complex chemistry requires. DNA, proteins, and other biological molecules would be destroyed faster than they could form or function. Even simpler forms of organization would be impossible. Crystals couldn't grow in such an environment because thermal motion would be too violent to allow ordered structures to persist. The temperature would be so high that all matter would exist as plasma, with electrons stripped from atoms by the intense radiation field. Chemistry itself would be impossible because atoms couldn't maintain their electron shells long enough to participate in chemical reactions. The hydrodynamics of such a universe would also be fundamentally different. The radiation pressure from omnidirectional starlight would be enormous, creating forces that would prevent the gravitational collapse necessary for planet and star formation. Gas clouds couldn't condense under their own gravity because radiation pressure would blow them apart faster than gravity could pull them together. This means that in a universe with a truly bright night sky, not only would life be impossible, but the very structures that make life possible could never form in the first place. There would be no planets, no stable environments, no protected niches where complex processes could unfold. The universe would remain a hot, uniform plasma without the hierarchical structure of matter that characterizes our observable cosmos. The thermodynamics of such a universe would also prohibit the emergence of complexity. Life and intelligence require energy gradients, differences in temperature, and chemical potential that can drive organized processes. In a universe at thermal equilibrium, with radiation at stellar temperatures, no such gradients would exist. Everything would be at the same incredibly high temperature, eliminating the energy flows that power organized systems. This thermal uniformity would make the second law of thermodynamics an absolute barrier to complexity. Entropy would already be maximized throughout the universe, leaving no room for the kind of organized, low-entropy structures that characterize living systems. The universe would be stuck in a state of maximum disorder, unable to generate the patterns and processes that we associate with interesting phenomena. The psychological impact of such a universe, if somehow beings could exist to experience it, would be overwhelming. There would be no cycle of day and night to provide temporal rhythm. No stars would be visible as discrete objects because they would be lost in the overwhelming background glow. The concepts of distance, direction, and cosmic structure would be meaningless because everything would be uniformly bright in all directions. Navigation would be impossible without visible landmarks or directional cues. The sense of place that comes from recognizing patterns in the night sky would be absent. The universe would appear as an undifferentiated blaze of light, offering no information about cosmic structure or history. The rich tapestry of astronomical phenomena that has inspired human curiosity for millennia would be reduced to a featureless glare. Even if beings could somehow survive in such an environment, they would be unable to develop science or understanding of their cosmic situation. Astronomy would be impossible because there would be nothing to observe except uniform brightness. Physics would be limited to local laboratory experiments because the large-scale structure of the universe would be hidden behind the wall of omnipresent radiation. The development of technology would also face enormous barriers. Electronics couldn't function in such high-temperature environments. Metals would exist only as vapors, making mechanical devices impossible. The intense radiation would interfere with any attempt to create controlled electromagnetic fields or organized energy flows. Perhaps most profoundly, consciousness itself might be impossible in such a universe. The neural processes that underlie thought and awareness require delicate electrochemical gradients that couldn't be maintained at stellar temperatures. The molecular machinery of the brain would be destroyed by thermal motion long before it could perform its computational functions. This thought experiment reveals something remarkable about our actual universe. The darkness of the night sky isn't just an interesting puzzle to be solved by cosmologists. It's a prerequisite for our existence, a necessary condition that makes life and intelligence possible. The dark spaces between the stars aren't empty voids to be filled with light. They're essential features that allow the universe to support complexity and consciousness. The cooling that comes with cosmic expansion, the finite age that limits stellar radiation accumulation, the vast empty spaces that separate energy sources. All of these factors that create cosmic darkness also create cosmic habitability. We exist because the universe is dark, not in spite of it. The night sky's darkness is the signature of a cosmos fine-tuned for the emergence of complex structures and conscious observers. This realization transforms our relationship with the dark night sky. Instead of seeing it as empty space waiting to be filled with light, we can appreciate it as the fundamental prerequisite for our existence. The darkness isn't the absence of something important. It's the presence of something essential. It's the cosmic background that makes foreground possible, the silence that makes music audible, the emptiness that makes structure meaningful. When we stand under the night sky and marvel at the scattered points of starlight against the dark background, we're witnessing the precise cosmic conditions that make our observation possible. A universe bright enough to eliminate the darkness would also eliminate us. The dark night sky is thus both the greatest mystery in cosmology and the greatest gift the universe could have given to conscious beings seeking to understand their place in the cosmic order. Long before Heinrich Olbers posed his paradox, long before Edwin Hubble discovered cosmic expansion, long before astronomers understood the Big Bang, human beings gazed up at the dark night sky and felt something stirring in their souls. The darkness between the stars wasn't just a scientific puzzle waiting to be solved. It was a canvas for the human imagination, a vast empty space that cultures around the world filled with stories, myths, and meaning. The night sky's darkness didn't just make life possible, it made human consciousness possible, providing the psychological and spiritual backdrop against which our species developed its capacity for wonder, creativity, and transcendent thought. Imagine our ancestors tens of thousands of years ago, gathered around fires under the African savanna's star-filled dome. The darkness surrounding their small circle of light wasn't empty. It was alive with possibility. It held predators and prey, mystery and danger, the unknown territories that lay beyond the reach of firelight. But when they looked up, the darkness took on a different quality. It became a realm of permanence and pattern, where the same stellar configurations returned night after night, season after season, generation after generation. This celestial darkness provided humanity's first calendar, first compass, first glimpse of mathematical regularity in the natural world. The dark spaces between stars weren't barriers to understanding. They were the background that made stellar patterns visible and meaningful. Without darkness, the stars would be invisible against a bright sky. Without the contrast between light and dark, ancient peoples couldn't have developed the sophisticated astronomical knowledge that guided their migrations, predicted their seasons, and organized their societies. But the darkness did more than provide practical astronomical tools. It created the psychological conditions necessary for mythological thinking, the human capacity to see patterns and stories in the random arrangement of stellar positions. The constellation myths that every culture developed weren't just primitive attempts at star mapping, they were profound expressions of human creativity, ways of projecting meaning and narrative onto the vast emptiness of space. The darkness between constellation figures became as important as the star patterns themselves. In many mythological systems, this cosmic darkness represented the primordial void from which all existence emerged. The Greek concept of chaos, the Norse idea of Ginnunga Gap, the Aboriginal Australian notion of the dream time, all envisioned cosmic darkness as the fundamental creative principle, the pregnant emptiness from which gods, worlds, and consciousness itself arose. This mythological association between darkness and creativity reflects something deep in human psychology. Darkness has always been linked with the unconscious, with dreams, with the hidden realms of mind where new ideas and insights emerge. The dark night sky became humanity's first symbol of the infinite, the eternal, the unknowable depths of existence that lie beyond rational comprehension. Ancient cultures developed remarkably sophisticated ways of reading meaning into the patterns of light and dark across the celestial sphere. The Milky Way, that faint river of light crossing the dark sky, became a cosmic highway for souls, a celestial river where the dead traveled to their final destinations. The dark lanes that interrupt the Milky Way's glow weren't seen as empty spaces, but as cosmic landmarks, the hoofprints of celestial horses, or the shadows of cosmic trees. The Inca civilization of South America developed perhaps the most sophisticated system for interpreting cosmic darkness. They recognized not just bright constellation patterns, but dark constellations, regions of the Milky Way where cosmic dust blocks background starlight. These dark nebulae weren't seen as empty voids, but as the silhouettes of cosmic animals, a dark llama, a dark toad, a dark partridge moving across the star field as Earth rotated beneath the celestial sphere. This Incan innovation, seeing meaningful patterns in darkness itself rather than just in points of light, represents a profound insight into the relationship between presence and absence, between signal and background. They understood intuitively what modern astronomers would later discover, that the darkness of space isn't truly empty, but contains structure and meaning of its own. The development of poetry and literature was similarly shaped by humanity's relationship with cosmic darkness. The night sky provided poets with their most powerful metaphors for the infinite, the eternal, the sublime. From the Psalms of ancient Israel to the verses of contemporary writers, darkness and stars have been humanity's primary symbols for transcendence, for experiences that lift consciousness beyond the mundane concerns of daily existence. But it's not just the presence of stars that makes the night sky poetically powerful, it's the darkness that surrounds them. The contrast between tiny points of light and infinite darkness creates a visual metaphor for consciousness itself, for the way isolated moments of awareness shine against the vast, unconscious background of mental life. The dark night sky became humanity's first mirror, a cosmic reflection of the structure of consciousness. This psychological resonance explains why the darkness of space has always been associated with both terror and beauty, with both the unknown and the unknowable. The night sky simultaneously represents the ultimate frontier, the destination of human exploration and curiosity, and the ultimate mystery, the realm that will always exceed human understanding. The darkness makes the stars precious by making them rare, creating the scarcity that generates both wonder and longing. The development of religious and spiritual traditions was profoundly influenced by humanity's experience of cosmic darkness. The transition from day to night became a daily reminder of larger cycles, of the rhythm between manifestation and dissolution that characterizes existence at every scale. The darkness that followed sunset wasn't just the absence of solar light. It was a return to the primordial state from which light first emerged. Many mystical traditions develop practices specifically designed to take advantage of the psychological effects of darkness. Meditation under the night sky, contemplation of the stars, spiritual exercises performed in the absence of artificial light. All of these practices used cosmic darkness as a tool for expanding consciousness beyond its normal boundaries. The darkness didn't hinder spiritual development. It enabled it by removing the distractions of the visible world and creating space for inner illumination. The invention of artificial lighting fundamentally changed humanity's relationship with cosmic darkness. For the first time in human history, large populations could live their entire lives without regularly experiencing the dark night sky. The light pollution that now blankets most urban areas doesn't just hide the stars, it severs the psychological and spiritual connection between human consciousness and cosmic darkness that shaped our species for millennia. This disconnection from cosmic darkness may have profound implications for human psychological development. Studies suggest that people who grow up in light-polluted environments show measurably different patterns of creativity, different relationships with transcendent experience, different capacities for what psychologists call openness to experience. The darkness that nurtured human imagination for thousands of generations is disappearing from modern life. The digital age has created new forms of artificial brightness that compete with cosmic darkness for human attention. Screens glowing in darkened rooms, electronic devices that never sleep, the constant illumination of information and entertainment. All of these technologies create what might be called cognitive light pollution, flooding consciousness with artificial stimulation that makes the subtle influence of cosmic darkness harder to perceive. Yet something in human nature continues to respond to the dark night sky with the same sense of wonder that moved our ancestors. Even people who have never experienced truly dark skies report profound emotional responses when they encounter the Milky Way for the first time. There seems to be something built into human consciousness that recognizes cosmic darkness as home, as the natural background against which awareness itself emerges. Modern astronomy has revealed that this intuitive connection between consciousness and cosmic darkness has a literal truth. The carbon atoms in our bodies, the oxygen we breathe, the calcium in our bones, all of these elements were forged in the nuclear furnaces of ancient stars and scattered into the darkness of space when those stars died. We are quite literally made of star stuff, cosmic material that spent billions of years floating through the dark void before condensing into planets and eventually into living beings. This means that when we look up at the dark night sky, we're looking at our cosmic ancestry, the vast spaces through which the atoms of our bodies once traveled. The darkness isn't separate from us, it's part of our history, part of the cosmic journey that led from the Big Bang to the emergence of consciousness. We carry the darkness within us, just as we carry the light. The future of humanity's relationship with cosmic darkness remains uncertain. As our species spreads beyond Earth, as we establish permanent settlements on other worlds, we'll encounter night skies very different from the one that shaped our ancestors. Some planets will have multiple moons, creating complex patterns of light and shadow. Others will orbit binary stars, experiencing double sunsets and sunrises. Still others may have no moons at all, offering views of cosmic darkness uninterrupted by reflected light. These alien night skies will challenge human imagination in new ways, providing different canvases for mythological thinking, different backgrounds for the development of extraterrestrial cultures. The specific patterns of light and dark that shaped human consciousness on Earth may give way to new forms of cosmic inspiration as our species adapts to the varied night skies of other worlds. But regardless of where humanity travels in the cosmos, the fundamental relationship between consciousness and darkness is likely to persist. The capacity for wonder, for transcendent experience, for the kind of thinking that reaches beyond immediate practical concerns. All of these distinctly human traits emerged from our species' long relationship with cosmic darkness. They represent adaptations to a universe where vast empty spaces separate islands of light and warmth. The dark night sky thus serves as both our evolutionary cradle and our spiritual teacher. It shaped the neural pathways that make poetry possible, the psychological structures that generate religious experience, the cognitive capacities that allow us to conceive of infinity and eternity. The darkness between the stars isn't just the solution to Olber's paradox, it's the foundation of human consciousness itself. When we stand under the night sky today, we're participating in a practice that connects us to every generation of our ancestors, a form of cosmic communion that transcends cultural and temporal boundaries. The darkness that surrounds us surrounded them. The stars that inspire us inspired them. The sense of wonder that fills us filled them. In our response to cosmic darkness, we discover not just the nature of the universe, but the nature of ourselves, the cosmic heritage that makes us who we are. We have journeyed from Heinrich Olber's simple question about why the night sky is dark to the edges of cosmic understanding itself. What began as an astronomical puzzle has revealed truths about the universe so profound that they transform our entire relationship with existence. The darkness between the stars, that familiar backdrop we take for granted every night, carries within it the signature of cosmic birth, the promise of cosmic death, and the delicate conditions that make our brief moment of consciousness possible. The solution to Olber's paradox isn't a single answer, but a convergence of cosmic truths, each more startling than the last. The universe has a beginning, emerging from a Big Bang 13.8 billion years ago in a burst of light and energy that still echoes through space as the cosmic microwave background. The universe is expanding, carrying galaxies away from each other at ever-increasing speeds, driven by the mysterious force we call dark energy. The universe is young enough that light from its most distant regions hasn't had time to reach us, creating a particle horizon beyond which we cannot see. Each of these discoveries emerged from our attempt to understand cosmic darkness, and each revealed something fundamental about the nature of reality itself. The dark night sky isn't dark because space is empty. It's dark because the universe has properties that make darkness inevitable. We live in a cosmos that began in time, evolves through time, and will end in time, and the darkness we see overhead is the visible proof of this cosmic temporality. But knowledge brings both wonder and terror, and our understanding of cosmic darkness carries implications that should chill us to our core. The same cosmic properties that create the beautiful dark night sky also condemn the universe to an ultimate fate more desolate than any vision of hell humanity has ever conceived. The expansion that redshifts distant light beyond visibility will eventually carry every galaxy beyond our cosmic horizon. The finite age that limits the accumulation of stellar radiation also means that star formation will eventually cease, and the universe will grow cold and empty. We are living in the cosmic equivalent of a brief spring morning, surrounded by the flowering of stellar birth and galactic structure that will not last forever. The universe is barely 13.8 billion years old now, but the processes we observe today will continue for timescales that make cosmic history seem like an instant. Stars will burn for trillions of years. Stellar remnants will cool for quintillions of years. Black holes will evaporate over periods measured in numbers so vast they exceed human comprehension. In 10 to the 100th power years, when the last black hole has disappeared in a final burst of Hawking radiation, the the universe will enter a state cosmologists call heat death. Space will be filled with nothing but a thin soup of elementary particles and photons, all at temperatures so close to absolute zero that thermal motion becomes negligible. No complex structures will remain. No energy gradients will exist to drive organized processes. No information processing will be possible. This ultimate cosmic state represents darkness on a scale that makes our current night sky seem blazingly bright by comparison. The faint glow of the cosmic microwave background that currently fills space will be redshifted to wavelengths so long that its energy becomes essentially zero. Even the quantum vacuum fluctuations that create virtual particles will become rare events separated by vast intervals of absolute emptiness. Yet somehow the contemplation of this ultimate cosmic darkness brings not despair, but a strange form of comfort. The fact that we exist at all, that consciousness has emerged in a universe destined for such profound emptiness, seems almost miraculous. We are temporary patterns of matter and energy that have organized themselves into beings capable of contemplating their own cosmic situation. We are the universe becoming aware of itself, however briefly. The dark night sky thus becomes a kind of cosmic koan, a paradox that reveals truth through apparent contradiction. The darkness that makes our existence possible also reveals the temporary nature of that existence. The emptiness that allows stars to shine also foreshadows a future when no stars will remain. The silence that makes cosmic music audible also hints at an eventual eternal silence when the music stops forever. This paradox transforms our relationship with every moment of experience. Knowing that the universe will eventually return to darkness makes the current abundance of light precious beyond measure. Every star we see overhead is burning fuel that will never be replenished. Every galaxy visible through our telescopes is participating in a cosmic dance that will eventually end in isolation and darkness. Every moment of consciousness is occurring during a brief interlude between infinite periods of unconsciousness. But this knowledge of cosmic fragility also reveals the extraordinary nature of our current situation. Against all odds, in a universe dominated by empty space and destined for emptiness, complex structures have emerged. Galaxies have formed, stars have ignited, planets have condensed, life has appeared, consciousness has awakened. The fact that we can stand under the dark night sky and wonder about our place in the cosmos is itself one of the most improbable events in the history of reality. The darkness between the stars becomes a reminder of what the universe has overcome to produce this moment. For 13.8 billion years, cosmic evolution has been building toward conditions complex enough to support conscious observers. The same expansion that will eventually destroy all structure has been creating the conditions necessary for structure to emerge. The same cooling that will lead to heat death has allowed the formation of atoms, molecules, and the intricate chemistry of life. We exist because the universe found a way to create islands of order and complexity in an ocean of growing entropy. The stars that shine against the dark background are nuclear furnaces that convert the simplest elements into the complex ones needed for planets and biology. The galaxies that spiral through empty space are vast recycling centers that process stellar death into stellar birth across billions of years. The darkness that surrounds these processes isn't their enemy, but their enabler, providing the space and time necessary for cosmic creativity to unfold. This perspective transforms the apparent emptiness of cosmic voids into something precious. Those vast regions of space where almost nothing exists aren't failures of cosmic evolution, but prerequisites for it. The empty spaces between galaxies aren't voids to be filled, but the stage on which the cosmic drama of complexity and consciousness plays out. Without the darkness, there would be no light. Without the emptiness, there would be no room for structure. The terror and beauty of cosmic darkness thus become inseparable. The same cosmic properties that make the night sky dark also make life possible, consciousness possible, wonder possible. We should be terrified by the ultimate fate that awaits the universe, but we should also be amazed that anything meaningful happens at all in a cosmos destined for such profound emptiness. Standing under the star-filled sky, surrounded by the ancient darkness that has persisted since the universe became transparent, we find ourselves at the intersection of cosmic history and cosmic destiny. The light reaching our eyes has traveled for millions or billions of years through the expanding void, carrying information about distant stellar furnaces that may no longer exist. The darkness that frames that light stretches back to the moment when the universe first became cool enough for photons to travel freely through space. We are witnesses to a cosmic story that began with a burst of light from the Big Bang and will end with the gradual fading of the last stellar embers into absolute darkness. The chapter we're living through, the epoch of stars and galaxies and conscious observers, represents a brief but magnificent interlude in this cosmic narrative. The darkness reminds us that this interlude won't last forever, but it also shows us how extraordinary it is that the interlude exists at all. The night sky's darkness thus becomes both a scientific fact and a spiritual teaching. It tells us about cosmic expansion and finite age and the limits of observable reality. But it also tells us about the preciousness of existence, the fragility of complexity, the miracle of consciousness arising from quantum fields and stellar nuclear synthesis and billions of years of cosmic evolution. When we look up at the stars burning against the infinite dark, we're seeing both our cosmic ancestry and our cosmic destiny. The elements in our bodies were forged in stellar cores that died long before the sun was born. The atoms of our consciousness will persist long after the sun has burned out, cycling through future generations of stars until the universe grows too old and empty for star formation to continue. We are temporary arrangements of cosmic matter that have acquired the ability to contemplate our own temporality. We are patterns of information encoded in carbon and water that can decode the messages written in starlight and cosmic background radiation. We are the universe's way of looking at itself, however briefly, with wonder and understanding. The dark night sky is the gift that makes this cosmic self-reflection possible. Without the darkness, there would be no contrast to make the stars visible. Without the emptiness, there would be no space for complex structures to evolve. Without the finite age and expansion that create cosmic darkness, there would be no conditions suitable for the emergence of conscious observers. The darkness between the stars is thus revealed to be not the absence of something important, but the presence of everything that makes importance possible. It's the cosmic background that allows cosmic foreground to exist, the silence that makes cosmic music audible, the emptiness that makes cosmic meaning meaningful. As we stand beneath this terrifying and beautiful darkness, we are participating in one of the universe's greatest achievements. In a cosmos destined for ultimate emptiness, matter has organized itself into beings capable of understanding that destiny. In a reality where complexity is temporary and fragile, consciousness has emerged to appreciate both the complexity and the fragility. The dark night sky whispers to us of cosmic loneliness and cosmic wonder, of ultimate endings and extraordinary beginnings, of the vast scales on which the universe operates, and the precious moment of awareness in which we find ourselves. It reminds us that we are children of the cosmos, born from stellar death and destined to return to cosmic darkness, but blessed with the ability to contemplate our origins and our fate with wonder rather than despair. In the end, the darkness between the stars teaches us the most important lesson about existence itself. We are here now, conscious and wondering, in a universe that didn't have to produce consciousness at all. The fact that the night sky is dark makes our existence possible, and the fact that we can understand why it's dark makes our existence meaningful. We are the universe's gift to itself, patterns of matter and energy that can appreciate the cosmic story of which they are part. The stars burn bright against the eternal dark, and for this brief cosmic moment, we burn with them.